In this video, we're going to talk about a model called the model of Cournot competition. So we're going to be thinking about some game theory stuff. And we're going to be thinking about a particular model of oligopoly. If you think about the types of markets that we've been considering so far, and that you consider first in any principles of microclass or intermediate microclass, you usually talk about perfect competition and then you talk about monopoly, because those are kind of the ends of the competitive spectrum. And in neither of those cases do we have to think about firms worrying about what the other firms are doing. So with perfect competition, each firm is small compared to the size of the market. So the actions of any particular firm don't have any impact on the market. You don't need to worry about what the other firms are doing. You just need to worry about what's happening at your location. And if we're talking about monopoly, obviously there's no other firm. There's only one firm. So we haven't talked really about monopolistic competition, but that's like perfect competition with differentiated goods. And so the firms there are not really worried about, there's no strategic interaction. But if you have oligopoly, then we're talking about a type of market where there's a small number of firms. And in that situation, each firm would be large compared to the size of the market. And so the behavior of any one firm is going to have a huge impact on the other firms. So if you're a firm, now you have to think about what the other firms are going to do, because that directly impacts what you're going to be doing. It directly impacts the market. And so if you don't know what they're going to do, then you don't have any idea of what the price is going to be in the market and what kind of demand you're going to face. And so strategic interaction becomes very important. So we're going to be thinking about game theory. And if you've had any background in game theory, you may have already talked about maybe the prisoner's dilemma, which is usually kind of the starting point. And if you want to go back, you could find my videos on oligopoly. You could find my principles of micro video on oligopoly. I have some intermediate microeconomics videos where we talk about different models of oligopoly that we're going to think about. So if you want, take a look at those. If you think about game theory, what we study in game theory can be roughly divided into non-cooperative games and cooperative games. Non-cooperative games, the unit of analysis would be the firm or an individual person, an individual player. If we're talking about cooperative games, then we're talking about groups that are cooperating with each other. We're going to be thinking about non-cooperative game theory. And so one of the things that makes it a little bit challenging when you start thinking about oligopoly models and different models of game theoretical models of firm behavior is that there's no single model. What we're going to see is that the outcome depends on the rules of the game being played. It depends a lot. And so every different oligopoly model is different from every other model. And you can tweak one little thing and it can dramatically change the outcome. So we're going to spend our time thinking about three main models. We're going to talk about the Cournot model, we're going to talk about the Bertrand model, and then we'll talk about the Stackelberg model. For this video, we're going to be thinking about Cournot. So the characteristics of a game, there are going to be players. Those are going to be, in our case, firms, but you could talk about individuals playing a game. There are going to be rules of the game, and there are going to be strategies. And so each player is going to pick a strategy, and then they play the game, and then we get outcomes. So the strategies combine to provide outcomes for the players. And again, the rules matter a whole lot. We can have a game that's where all of the players have to make their decision at once, or we can have a game where it's sequential, where one person moves first or one firm moves first and then the next firm moves. One thing that we really need to think about, though, one concept that is extremely important is the concept of the Nash equilibrium, named after an economist, mathematician, statistician, a person named John Nash, an incredible academic that did a lot of interesting work in a lot of different fields, but he won the Nobel Prize in economics for his work in economics on Nash equilibrium. He wasn't the first game theorist, but he took the work that a lot of people had done and really did some interesting stuff. So let's talk about a Nash equilibrium and what it is. A Nash equilibrium is simply an outcome where all of the players are satisfied with the strategy that they chose, given the strategies that the other players chose. Another way to say it would be that no player would wish to go back and change their strategy, given what everybody else did. Now, it's important to realize that the Nash equilibrium may be a good place to be for the players. It may not be a good place to be for the players. So the Nash equilibrium is not necessarily where everybody's as well off as they could be. That's not it. It's simply a situation where, given what everybody else did, you made the best choice of strategy. What we're going to be thinking about, the strategies that our firms are going to be thinking about are choosing how much output to produce, or maybe choosing the price that they charge for the output that they produce. And what we're going to see is that models where firms choose output have very different outcomes than models where firms choose price. So the basic idea behind a game, the way that a firm would work its way through a game, is that they've got to decide what the other firms are going to do, and then decide, given what we think that firm's going to do, what's it in our best interest to do. One way that we think about solving a game is that we can think about dominant strategies. You can also think about dominated strategies. So let's start with a dominant strategy, or dominant strategies. Usually I'm going to think about that as just a dominant strategy. A dominant strategy would be a strategy where that's always the best strategy to play, regardless of what the other person does or the other firm does. That would be a dominant strategy. A dominated strategy would be a strategy that's never the best strategy to choose, regardless of what the other firm does. A dominated strategy, you could just eliminate it from the game because nobody would ever play that. Let's work through an example. Let's consider two airlines. So we'll think about Delta and American Airlines. And let's suppose that each of them offers a daily flight. It's a long flight, say from Boston to Budapest. And they can choose to depart either in the morning, where they would leave in the morning and get to the location, the destination in the evening, or they can have an evening departure. Where they leave in the evening and they get there the next morning. Okay, so Delta has to decide, do we want to leave in the morning or the evening? And American has to make the same decision. Let's suppose that our consumers have preferences over the departure time. So in terms of consumers, let's suppose that 30% prefer morning, 70% prefer evening. Let's suppose that if the two airlines depart at the same time, so if both of them depart in the morning, then they're going to split this market. If both of them depart in the evening, they're going to split that market. Okay? So now, we're going to create what I'm going to refer to, and a lot of books refer to, as the game matrix. So essentially what that is just a matrix, and I'm using the word matrix there in the matrix algebra sense. We're going to put American up here. And American has two strategies. I'm going to divide this matrix into two columns that correspond to the two strategies that American Airlines have. and that's going to be leave in the morning or leave in the evening. And then over here on this side, we're going to put delta, and we're going to divide it into 2 rows. And those 2 rows are going to correspond to the strategies that delta has, which are the same. They can leave in the morning or leave in the evening. Now, different textbooks do this next step differently. I like to do it this way. I'm going to divide my boxes into 2 halves like this. And I'm going to put the payoffs in each half. Now, this top half is going to be the payoff that goes to American, and the bottom half is going to be the payoff that goes to delta. Some books do it with 2 numbers with a comma in the middle. That's fine. I like this. It's easy for me to keep track of what's going on this way. Now, let's suppose they both leave in the morning. Let's suppose that the profits that the firm earns, it's proportional to the number of flyers that they carry. So we don't have to worry about dollar amounts. We can worry about these percentages. So let's suppose that if both of them leave in the morning, they're going to split this 30% right here. So let's suppose 15% goes to each. And if they both leave in the evening, they're going to split this chunk of the market, the 70% of consumers who want to leave in the evening. And so they split 70. That means they each get 35. But now, if one of them leaves in the morning and the other one leaves in the evening, then the one that leaves in the morning is going to get the 30%, and the one that leaves in the evening is going to get the 70. So what I've got here is delta leaving in the morning, they get 30% of the market. American leaves in the evening, they get 70%. If delta leaves in the evening, they're going to get the 70%, and American, which is leaving in the morning, would get the 30%. So there's the payoffs depending upon the strategies that are chosen by each of our 2 players. So let's start by considering the point of view of delta. Okay, so let's think about delta's point of view. Delta knows that American can either choose morning or evening. Let's suppose that American chooses morning. Well, then delta is either going to get a payoff of 15% or a payoff of 70%. So if American chooses the morning strategy, then delta's better off choosing 70. Choosing evening. On the other hand, American could choose evening, in which case delta's either going to get 30% of the market or 35% of the market. It would prefer the 35, so it's going to choose evening. So what we've seen is, if American chooses morning, delta likes evening. If American chooses evening, delta likes evening. This is a dominant strategy for delta. And if you work through it by taking the point of view of American, you'll see that the evening departure is also a dominant strategy for American. So what we could say is the likely outcome is for both of them to choose that evening departure. That would be the likely outcome in this game. They split the market. It is also the Nash equilibrium of the game. If you look at this and you say, okay, both of them chose the evening. Let's take the point of view of delta. Delta chose evening. Delta sees that American chose evening. Does delta wish that it would have instead chose morning? Well, if American had chosen the evening, as they did, and delta chose morning, they would be worse off. So they don't regret their strategy. Neither of them would regret the strategy. It's not always the case that a firm has a dominant strategy, but when they do, you don't really have to think about the strategic interaction very much. They just play their dominant strategy. Let's do an example where one of the firms does not have a dominant strategy. So let's change it a little bit. Let's say that because there's a frequent flyer program, that some flyers prefer delta, even if the 2 of them fly at the same time. So let's have a game matrix where we have it payoffs be a little bit different. So we're going to again have American up here. We're going to have delta. They can leave in the morning or evening. I'm going to abbreviate those M and E, morning and evening. And let's suppose if both of them leave in the morning, remember Delta has the frequent flyer program, so some customers are going to fly Delta because of that. Let's suppose they split the market, but it's not an even split. Let's suppose Delta gets 18 and American gets 12% of the market. And if they both leave in the evening, let's suppose Delta gets 42% of the market and American gets 28% of the market. If they leave at different times, if Delta leaves in the morning and American leaves in the evening, then they still split the market and it looks like this. So it's a similar set of payoffs, but our main diagonal elements are going to be different. Now what we can do, we can see that Delta still has a dominant strategy, right? If American chooses morning, then Delta's either going to get 18 or 17. It would rather leave in the evening and 70, would rather leave in the evening and get 70. If American chooses to leave in the evening, Delta would rather leave in the evening. But American has no dominant strategy. If you can see that if Delta leaves in the morning, then American would rather leave in the evening. But if Delta leaves in the evening, American would rather leave in the morning. It'd rather have the 30 over the 28. So American has no dominant strategy. The outcome's still clear though, because Delta's always going to choose evening. If you're American and you're a decision maker, you would say, well, we don't ever have to worry about Delta choosing morning because evening is a dominant strategy. Morning is a dominated strategy. So given that Delta is going to choose the evening departure, American would rather leave in the morning. So our likely outcome is right there for this game, where Delta leaves in the evening, American leaves in the morning, and they have those payoffs. And that's also a Nash equilibrium in the game. It's a game where neither of them would wish they had changed their strategy or chosen a different strategy. There are games where no dominant strategies exist. And in that case, one way that you can solve the game is just take each particular outcome and see if it's a Nash equilibrium. And you can do that until you find a Nash equilibrium, if there is one. That's a possible method of solving these. Identifying dominant strategies or dominated strategies can be much quicker than evaluating whether or not each thing is a Nash equilibrium. Let's think about a different game where we have firms choosing prices. So let's suppose a firm can choose, same two firms, American and Delta, but now they're choosing price and they can choose a low, medium, or high price. So let's suppose we have a little bit bigger game matrix because now they're each going to have 3 strategies. We're going to put American up here again. We'll put Delta over here. And now we've got American having the strategies of low price, a medium price, or a high price. And the same with Delta. We'll put here a low price, medium price, or a high price. And I'm going to divide these in half. And let's put our payoffs in here. Let's suppose that if they both charge the low price, let's suppose they get 15,000. I'm going to write 15K for 15,000 instead of writing all those zeros there. If they both have a low price, they each earn 15,000. If they both have a medium price, they each earn 35,000. I'm going to skip the K's from now on. If they both charge a high price, they both earn 30. And then let's put these off diagonal. Let's suppose that Delta charges a low price and American charges a medium price. Then let's suppose Delta gets 25 and American gets 22. So because Delta has a lower price, they're able to steal some market share. On the other hand, if Delta charges a low price and American has a high price, let's suppose Delta gets 40 and American gets 20. They steal even more market share. Suppose if Delta charges a medium price and American a low price, it's going to be 22 and 25. Delta loses a little bit to American. If Delta has a medium price and American has a high price, let's suppose it's 38, and 33. And then down here we'll have kind of the mirror image of what's happening up there. So there's some payoffs. We could check cell by cell to see if a particular cell is a Nash equilibrium. The way you would do that is you would say, okay, let's check this one. Here, Delta has chosen a high price and American has chosen a low price. Well, let's start with Delta. Delta, American chose low, so we're in this column. Delta would either get the 20, the 22, or the 15. It would rather have the 22 than the 20. So it regrets its strategy. It would rather switch from high to medium. So that can't be a Nash equilibrium. So you could go through that and identify whether or not each cell is a Nash equilibrium. What you would see is that the Nash equilibrium of this game is where each of them identify or choose a medium price. That's the only Nash equilibrium. It's the only situation where neither of them would switch strategies if they could, given what the other firm did. Another way that you could do this is you could identify that choosing the high price is a dominated strategy. It's a dominated strategy for both Delta, right? Deltas would never choose the 20 over 22 or 33 over 35 or 30 over 38. These three payoffs are lower than those three payoffs. And so you could eliminate this and you could eliminate that. That leaves you with a 2x2 game. So you could start to eliminate dominated strategies and you would get that same Nash equilibrium. I'm telling these stories as if there's some back and forth that's going on, but if you're the decision maker in these firms and you know what this game looks like, there's no back and forth. You would choose these strategies, these likely outcomes, as the best possible choice for you, given what the other firm's going to do. So that gives you some idea, hopefully, of kind of a refresher on games where we choose quantity or games where we choose price, and why the Nash equilibrium is such a useful concept. What we want to do now is talk about the Cournot model. So the Cournot model was first developed by an economist, French mathematician actually, named Augustin Cournot. It was published in 1836. It was pretty much unrecognized or not recognized as the important work that it was for 100 years. But here's the idea that Cournot laid out in the first paper. And that was that suppose there's a monopoly in the market. And then there's another firm that desires to enter that market. And let's suppose that the new entrant's product is identical to the monopoly's product. And the new entrant is going to have an incentive to enter because the monopoly is making a profit from what they're selling. Let's suppose the new entrant would have the same costs of production. And so because the monopoly is able to charge a price higher than marginal cost, the new entrant would also. So there's an incentive for the entrant to enter the market. What Cournot recognized is that the new entrant would take into consideration how much output the monopoly is producing already in their choice of output. Cournot also recognized that once the monopoly would recognize the new entrant's quantity that they would produce and would react to that. So the entrant would first react to what the monopoly is already producing, and then once they've entered, the monopoly would react to the entrant. And Cournot identified the fact that you could graph these reactions, and he called them reaction curves. You can graph that in terms of the space of how much each firm produces, and I'll show you that here in a second. So Cournot identified the equilibrium in the model as the pair of output levels at which each firm's output is the profit maximizing response to what the other firm is doing. Now, if you listen to that and think about it, that is a almost identical concept to the Nash equilibrium, right? It anticipated Nash's equilibrium. The other neat thing about the Cournot model is that it predicts an outcome for oligopoly that falls in between perfect competition and monopoly, which is intuitively very pleasing. And we'll talk about that also. So let's work through the Cournot model. It's a very straightforward model to work through. So let's suppose we have two firms, and each firm is going to choose the quantity of output to produce, and they're going to make that decision simultaneously. Let's suppose that the market demand curve looks like this. P equals A minus B times Q. Now, this is going to be an inverse market demand curve because it's solved for P. And that quantity is the quantity produced by firm 1 plus the quantity produced by firm 2. So where this quantity is equal to little q1 plus little q2. So we can plug that in. We would say that P is equal to A minus B times q1 plus q2. And we could distribute that B through. We get this P equals A minus B q1 minus B q2. So there's the inverse market demand curve. Let's consider the perspective of firm 2 first. So from firm 2's perspective, these two terms right here are out of its control. Firm 2 doesn't have any control over those two things. From the point of view of firm 2, these are just the intercept of the demand curve, right? Firm 2 has no control over the amount of output that firm 1 produces. Firm 2 gets to choose its output. So when we think about the demand curve that firm 2 faces, we can think about it as what we would refer to as a residual demand curve, right? And it's affected, the demand curve that firm 2 faces is in part determined by how much firm 1 produces. So the demand curve that firm 2 faces has as its intercept this, A minus B times Q1. And the more Q1 produces, the smaller the demand that firm 2, or the more that firm 1 produces, the smaller the demand that we as firm 2 face. Okay? So this is the demand curve faced by firm 2. Of course, firm 2 seeks to maximize profit. So what we need, this is the demand curve that firm 2 faces. We need the marginal revenue because we know that profit maximization means that the firm is going to produce the quantity where marginal revenue equals marginal cost. So we can write the marginal revenue curve. Here's the slope of the inverse demand curve. And so remember that the marginal revenue curve has the same intercept, which would be A minus B times Q1, and twice the slope, minus 2B Q2. There's the marginal revenue curve that firm 2 faces. We're going to let marginal cost equal C. So the firm is going to set marginal revenue equal to marginal cost. We're going to get this, A minus B Q1 minus 2B Q2 equals C. And now we need to solve for Q2. So we're going to solve for this. I'm going to move it to the other side, and then I'm going to switch some things around. So I'm going to get 2B Q2 equals A minus C minus B Q1. I did several steps all at once there, so make sure you understand what's happening there. I'm going to divide through, I need just Q2, so I'm going to divide through by 2B. I'm going to get Q2 equals A minus C minus B over Q1 divided by 2B, which I can simplify as, that should be Q2, A minus C over 2B minus Q1 over 2. That's important right there. That equation describes firm 2's best choice of output as a function of the parameters of the demand curve and the amount of output that firm 1 produces. And you can see the more that firm 1 produces, the less firm 2 is going to produce. I can go through the same process for firm 2, or excuse me, for firm 1. It will all be symmetrical, so what we're going to get for firm 1 is A minus C over 2B minus Q2 over 2. I'm going to put a little star right there. What we're going to do is we're going to graph these things. These show us, essentially these are the reaction curves that we were talking about. How firm 2 is going to react to what firm 1 produces, and how firm 1 is going to react to what firm 2 produces. So I need to clear this off, and then we'll graph these. All right, let me rewrite these over here together. So we've got our reaction curves. Q2 is equal to A minus C over 2B minus Q1 over 2. And Q1, A minus C over 2B minus Q2 over 2. I'm going to graph these in this space where I've got Q1 down here and Q2 up here. Now let's start with this one because it's easy to graph. It's already solved for the thing that I've got on my vertical axis. So that means that the intercept of this reaction curve is A minus C over 2B, and its slope is negative 1/2 because here's my other variable. Here's Q1, which I've got on the horizontal axis. So this thing looks like this. It's A minus C over 2B, and it comes down, and it looks like that. That is firm 2's reaction curve. Firm 2. Now, in order to solve or to graph this one, we would need to invert it, right? We would need to solve it for Q2. I'm not going to go through that process. You can do it, but I'm going to show you what it's going to look like because we can also just think about inverting this and then graphing. It's going to end up being, it's going to hit right here and right here. It's going to look like this. This problem is symmetrical. So this is also A minus C over 2B. And this intercept up here is actually A minus C over B. And this one's A minus C over B. This is, let's say, this is half the amount of that. Okay? That's where that 2 comes from. Okay, so there's, this one's firm 1. Now, let's think about what this tells us. This is a different way to look at the problem than the game matrices that we were looking at just a little bit ago. But it's still a way that you can identify the place where each firm is going to be satisfied with its strategy. Let's start by thinking about this. Let's suppose we start with firm 1 producing the monopoly outcome. If you solve this thing and you figure out, go back with that demand curve, pretend it's a monopoly, find its marginal revenue curve, set it equal to marginal cost, and solve for quantity, you're going to get this quantity. So that would be the monopoly quantity. Let's suppose firm 1 is the monopoly producing that quantity at A. And then firm 2 all of a sudden enters the market. Well, this is firm 2's reaction curve. And what it tells us is that if firm 1 is producing this quantity, then we go up to the reaction curve. It tells us that firm 2 should produce this quantity. Right there, that amount. So I'm going to call that point B. But then, if firm 2 is producing this quantity, if we go back to firm 1's reaction curve, firm 1 would prefer that quantity. Right there on its reaction curve. I'm going to call it point C. But then if firm 1 is producing at point C, firm 2 would prefer that quantity. And you can see what we're getting is we're getting closer and closer to that point right there, which it turns out is the Nash equilibrium of the game. That's the only place where each firm's output is the optimal response to what the other firm is producing. Remember, that's how Cournot identified the equilibrium. He described it as the place where each firm is producing the profit-maximizing quantity given what the other firm is doing. If we were right there at that intersection of the two reaction curves, then both firms would be happy with their strategy, happy with the quantity they're producing, given what the other firm is doing. So what we are doing by looking at this graphically is essentially we're finding the intersection of these two curves. Okay? So if we have these two curves, 1 and 2, there's two functions and two unknowns. You can easily solve that. Okay? I'm not going to go through it, but here I'm going to set it up, and you could work through the algebra if you want. But if we were to take and plug, let's say plug equation 1 into equation 2, the way that would look would be this. If we plug equation 1 into equation 2, we would have this. Q1 equals A minus C over 2B minus, I'm going to pull that 1/2 out, minus 1/2 times Q2, which Q2 is A minus C over 2B minus Q1 over 2. And now you can see we've got a statement that only has Q1 in it. You can easily solve that for Q1. It would require a little bit of algebra, but it's not hard algebra as long as you're careful. And what you're going to get is you're going to get this. Q1 is equal to A minus C over 3B. That's going to be that intersection. It's going to be Q1. And we're also going to get Q2. Once you get Q1, you can plug Q1 right into there. And what you're going to get is, for Q2, is you're going to get A minus C over 3B. Remember, this problem is symmetrical, so you're going to get the exact same number for each. Let's put a star there. I would encourage you to work through that and just verify that that's the optimal quantity for firm 1 and firm 2 to produce. Total output is the sum of these. So total quantity, which I'll call Q star, is just A minus C over 3B plus A minus C over 3B, which gives you 2A minus C over 3B. That's the market quantity. That's the total amount produced in the market. Once you've got that total quantity, you can plug that into the original demand curve. Remember, our demand curve is just P equals A minus B times Q. Well, if you plug that in, that Q right there, what you're going to get is you're going to get this. P star is equal to A plus 2C over 3. You can figure out profit. Again, I would encourage you to work through the algebra of doing it, but here's what you're going to get for profit. This will be profit for firm I, so it'll be 2, profit for firm 1 and profit for firm 2. It's going to look like this, A minus C squared over 9B. Now, keep in mind that Cournot's story makes it sound as if there's this back and forth decision making, one firm reacting to the other firm. That's the story that Cournot told. What we know, though, is that the concept of the Nash equilibrium is powerful enough that there would not need to be a back and forth. If there are two firms in the market, the managers might play the game out in their head, but the managers would realize that this outcome, these quantities right here, are the quantities that they need to produce, because they're going to know that the other firm is going to be able to think through this process. So what we do is we've changed the names of these. Over time, these have come to be referred to as best response curves or best response functions. So that's the terminology that I'm going to be thinking about, best response functions, rather than reaction curves, because they're not reacting. It's a process that they can think through. So I can't guarantee that I won't accidentally call them a reaction curve or a reaction function, but I'm going to try to remember that. Let's think about a numerical example. So this, especially the algebra of this, can be more challenging to work through if you're doing it in general like this with A and B. A lot of times when you have just plain numbers, it's very quick to work through. So let's work through an example. Let's suppose we have two firms. Let's suppose our market demand curve looks like this, 200 minus 40Q. So here, A is equal to 200 and B is equal to 40. Right? And so let's suppose that our cost is equal to 40 also. Now what you could do is you could just plug in, we know that, let's just write out here, A is equal to 200, B is equal to 40, C is equal to 40. So you could plug A, B, and C into each of these things and easily, in no time, come up with your answers. But let's work through it. So firm 1 faces, let's identify the demand curve faced by firm 1. It would be P equals 200 minus 40Q2 minus 40Q1. Which means that the marginal revenue curve for firm 1 would be equal to 200 minus 40Q2, same intercept, minus 80Q1. So it has the same intercept and twice the slope as the demand curve that it faces. I'm going to set marginal revenue equal to marginal cost. My marginal cost is 40 equal to marginal revenue. 200 minus 40Q2 minus 80Q1. So what I'm doing is marginal cost equals marginal revenue. And then we're going to work through that algebra. We're going to get, I'm going to move my Q1 over here so I get 80Q1. I'm going to move that 40 to this side and subtract it from 200. That's going to leave me with 160 minus 40Q2. And then I'm going to divide through by 80. I get Q1 equals 2 minus Q2 over 2. That's for Q1. That's my best response function for firm 1. You could go through this same process for firm 2. The algebra would be the same. In fact, the numbers would be the same, and you would get this, Q2 equals 2 minus Q1 over 2. There's my best response function for firm 2. So if you were to plug A, B, and C into these things, that's what's going to pop out of there. let's plug one of these into the other. So let's say Q1 is equal to 2 minus 1/2 Q2, and Q2 is equal to 2 minus Q1 over 2. So it's equal to 2 minus 1/2 times 2 is 1 plus Q1 over 4. There's Q1. So I get, let's say Q1 minus Q1 over 4 is equal to 1. That's 4Q1 over 4. So 4Q1 over 4 minus 1 of them is equal to 3Q1 over 4 equals 1Q1 equals 4/3. The algebra is not hard. That means that Q2 is also equal to 4/3. And total quantity is the sum of those. It's equal to 8/3. I can get price, right? Price is equal to 200 minus 40 times my total market quantity, which is 8/3. Right? Do a little bit of algebra. You're going to get 280 over 3, which is equal to 93.33. That's my market price. Profit would be price times quantity, total revenue minus total cost. Price times quantity. Remember, we're going to do this for a firm, so we got to think about the quantity as being the quantity that one firm produces. I guess you could calculate total profit and then divide it in half to get firm quantity or firm profit. But it's going to be the quantity 4/3 times price, which is 280 over 3. There's total revenue. Minus total cost would be the quantity that they produce, 4/3 times my marginal cost, which would be 40. Our profit would be 71.111. There's profit for firm I. And again, if you were to plug in A, B, and C into these, you can verify that those are correct. So let's compare this to the monopoly outcome. Okay, so we know how much each firm in the Cournot situation is going to produce. We know the price in the Cournot situation, and we know the profit. So I'm going to draw a little box here, and let's just figure out what monopoly would look like. Remember, monopoly, the demand curve would look like this. P equals 200 minus 40Q. The marginal revenue curve would be equal to 200 minus 80Q. There's marginal revenue. I can set marginal revenue equal to marginal cost. So 200 minus 80Q equals 40. That's my marginal cost. That means that 80Q equals 160. Q equals 2. So if this was a monopoly, the monopoly would produce 2 units. And if we plug that 2 back in here, it's going to be, price is going to be equal to 200 minus 40 times 2. 200 minus 80. Price is going to be equal to, what's that, 120. Price equals 120. So there's our monopoly outcome. Let's do our perfect competition outcome. That one's easy because it's just price equal to marginal cost, right? Anytime you're finding perfect competition, you set price equal to marginal cost. So that's 200 minus 40Q equals 40. You get Q equals 4. And of course, they're going to charge the price equal to marginal cost, which is 40. So there's the monopoly outcome, the perfect competition outcome, and you can see that the oligopoly outcome falls right in between these two quantities, 2, 4. That quantity of 8/3 is right in between those. And our price falls right in 93 with oligopoly, falls right in between perfect competition, which is 40, monopoly, which is 120. What I need to do now is clear this off, and we're going to think about some variations. We can generalize this model to do some neat things. So let's do that. One of the variations that we can do with the Cournot model is we can think about what happens if you change the number of firms. So the question is, we've just seen that the Cournot model generates a predicted outcome that falls in between perfect competition and monopoly. What happens as we increase the number of firms? What if there were 3 firms or 5 firms or 10 firms? Is it the case that we get closer to perfect competition? Because the difference between perfect competition and monopoly is really the number of firms. So that's what we want to do. We want to think about changing the number of firms in the model and then think about whether we get closer or farther away from perfect competition. Let's suppose we have n identical firms. And let's continue with our assumption that they have identical marginal costs equal to C. Our industry demand is still going to be P equals A minus BQ. But now that quantity is going to be summed across n firms, right? And so we've got quantity equal to Q1 plus Q2 plus out to Qn. And we can write that as summation notation, I equals 1 to n of Qi. So we're just adding up Q1 plus Q2 plus Q. Let's make that a capital N, since that's the notation I used. Now, let's think about firm 1. Okay, so consider firm 1. If we think about the demand curve that firm 1 faces, it's going to be very similar to what we saw before, except that intercept is going to be bigger. So from firm 1's perspective, the demand curve that it faces is A minus B Q2 minus B Q3 out minus out to B Qn minus B Q1. So this should be an N right there. That's the demand curve that firm 1 faces, where all of this stuff right in here represents the intercept. The firm 1 has no control over any of the quantities produced by the other firms. Now, what we can do is we can come up with some notation that kind of simplifies that. So let's let Q minus 1 represent the industry output other than firm 1. So that's the amount made by all the firms except firm 1. We're subtracting off firm 1 there. And so what we can do is we can write it this way. Now that allows us to write A minus B big Q negative 1 minus B Q1. And now it doesn't feel quite so intimidating. What we can then do is we can write firm 1's marginal revenue curve. Marginal revenue 1 is equal to A minus B, forget that, Q negative 1 minus 2B Q1. We set marginal revenue equal to marginal cost. So we're going to set A minus B Q negative 1 minus 2B Q1 equal to C. And we're going to solve that for Q1. It's easy to do. I'm going to skip that step. What you're going to get is this. You're going to get Q1 equals A minus C over 2B minus Q negative 1 over 2. Something that looks very similar to what we just saw when we had only two firms. In fact, the best response function for firm I, call that Q star, would be equal to A minus C over 2B minus Q negative I over 2. So that's what the best response function is going to look like. That would be for I equals 1 out to N. Now, in terms of solving that, that's a bigger system of equations, but we don't need to go through all of that. All of our firms are identical, so total industry output, total quantity would be equal to N times Q star, which means that this term right there, Q, or let's treat that term right there, Q negative 1 would be equal to N minus 1 times Q star. All right, if we pull out one of the firms, then this term right there is going to be N minus 1 times Q star. And solving for Q star, solve for Q star, what we get is that Q star is equal to A minus C over N plus 1 times B. That's the quantity produced by a firm. All of our firms are identical, so if you figure it out for one firm, you've got it for all of them. Industry output is N times this, so industry output Q is equal to N, number of firms, times Q, that, which is equal to N A minus C over N plus 1 times B. If you do a little bit of algebra, you plug that into the demand curve, you can get price. I'm going to skip that because it's easy, but price is equal to A over N plus 1 plus N over N plus 1 times C. Now, let's think about those. If you think about, let's start with output here. The perfect competition, if you just set price equal to marginal cost, so A minus B Q equals C, and you solve for Q, what you're going to get is that Q equals A minus C divided by B. A minus C divided by B. This chunk right here, that's the perfect competition output right there. And here's what this says. This says that if we have N firms, we can plug in what's happening. We can plug in, let's say we have one firm. Then that means that the quantity, the monopoly quantity, would be 1 over 2. It would be 1/2 the perfectly competitive quantity. If you have two firms, it's going to be 2/3 the perfect competition quantity. If you have three firms, it's going to be 3/4 the perfect competition quantity. So as you increase the number of firms, if we were to increase this, we're getting closer and closer to the perfect competition quantity, which means that question of, as we increase the number of firms, do we get farther or closer away to perfect competition? In terms of quantity, we're getting closer, which makes sense. That's intuitive. In terms of price, remember, with perfect competition, the price would be equal to marginal cost, which is right there. Well, as we increase the number of firms, this thing goes to 0, right? As N goes up, since it's in the denominator, that thing's vanishing. And as N goes up, this is getting closer and closer to C. If we just have one firm, it's going to be 1 over 2. This chunk right here would be 1/2 C. There would also be some stuff right there, but let's focus on this term. as we increase to 2 firms, it'd be 2/3 times C, and 3/4, and 4/5, and 5/6. And as n goes up, this is just getting closer and closer to C. So we can see that as we increase the number of firms, we get closer and closer to perfect competition, both in terms of quantity and in terms of price. Another thing that we can do, another way we can generalize this model, is we can think about what happens if the firms have different marginal costs. We've assumed it's identical. It doesn't have to be. So let's suppose we have 2 firms, and let's say firm 1 has marginal cost equal to C1, and firm 2 has marginal cost equal to C2. Okay. For firm 1, let's start with firm 1. What we can do is we can say, okay, firm 1, the price or the demand curve that they face is A minus B Q2 minus B Q1. We've already done their marginal revenue would be equal to A minus B Q2 minus 2B Q1. Same intercept, twice the slope. We set that equal to marginal cost, which for firm 1 is C1. What you're going to get, I'll skip the simple algebra there, what you're going to get is this. Q1 star is equal to A minus C1 over 2B minus Q2 over 2, which you probably could have guessed that that's what you were going to get. It's very similar to what we were already seeing, except instead of just C, it's C1. And for Q2, firm 2, you're going to get A minus C2 over 2B minus Q1 over 2. So it turns out pretty much like you would expect. Now let's think about what this means. Let's look at our reaction, or excuse me, our response functions. So we've got Q1 here, and we've got Q2 here, and we've got our firm 2 response function, and we've got our firm 1 response function, and right there's our equilibrium to begin with. Let's suppose the marginal cost for firm 2 increases. Suppose C2 increases. Well, let's think about what's going to happen to this response function. If C2 increases, that means his numerator here is getting smaller, which means Q2 is going down. This thing is shifting down if marginal cost gets bigger. Our intercept there is getting smaller. And so what would happen is we would move from a Nash equilibrium here, let's call it little a, to a new Nash equilibrium right down there, which means that if marginal cost is increasing for firm 2, that means that, let's see here, its intercept is decreasing, right? Firm 2 is producing less since its marginal cost is going up. Firm 2's output is going down, and firm 1's output is going up, which makes perfect sense, right? If it's more costly for firm 2 to produce, they're going to produce less. We can also, let's see, if we were to solve this system of 2 equations, let me just write what the optimal quantities are going to be. Q1 star is equal to A plus C2 minus 2C1 over 3B. And the optimal quantity for firm 2 is equal to A plus C1 minus 2C2 over 3B. That's the optimal quantity. So if in a problem you were given C1 and C2 and you knew what the parameters of the demand curve were, You can easily just plug those in and figure out what the quantity is that each firm produces, but this also allows you to see what happens if marginal cost goes up for firm 2. If marginal cost goes up for firm 2, firm 1 produces more output and firm 2 produces less output. That increase in C2 is subtracting away from the numerator up there. Let's work through this with our numerical example, because it's very easy to change C1 and C2 in that numerical example and see what we get. So we have P equals 200, our demand curve, minus 40Q. There's our demand curve. Let's suppose that C1 is equal to 40 and C2 is equal to 20. This time, let's decrease C2. Let's have C2, firm 2, have a lower marginal cost. Then if you work through that, let me just set it up for you. So for firm 1, what you're going to get is that it faces a demand curve that looks like this, 200 minus 40 Q2 minus 40 Q1. Its marginal revenue curve would be 200 minus 40 Q2 minus 80 Q1. And then you would set that marginal revenue equal to its marginal cost, which is 40. So 40 equals 200 minus 40 Q2 minus 80 Q1. What you're going to get out of that when you work through it is Q1 is equal to 2 minus Q2 over 2. There's the response function for firm 1. Now you're going to go through the same process for firm 2. And it's going to look very similar, only when you set it equal to marginal cost, you're going to have 20 there. And when you do that, what you're going to get is you're going to get a response function for firm 2 that looks like this. It's equal to 9/4 minus Q1 over 2. If you plug in, you could solve that system of 2 equations and 2 unknowns. You could solve it, or you can plug in the A, B, and C's into it. What you're going to get is Q1 star. The optimal amount for firm 1 to produce is 7/6, and the optimal amount for firm 2 to produce is equal to 5/3 or 10/6. Let's write it that way. That way it's easier to see that firm 2 produces more than firm 1. So, not surprisingly, the firm with the lowest marginal cost produces the highest quantity. You could go through and you could plug in the A, B's, and C's to get your prices, and you could figure out your optimal, actually it's easier than that, figure out your optimal quantity by adding these up. You can plug that into your demand curve to figure out price. It's all relatively straightforward. One thing that we know in this case, though, is that the total quantity, which is going to be 17/6, the total quantity produced in the market is produced inefficiently. And we know that because if you think back to the first equal marginal principle, what it tells us is that if we're minimizing costs, what comes out of that is a statement where a bunch of marginal things are going to be equal. And if we're minimizing cost, that tells us that marginal cost for firm 1 and marginal cost for firm 2 will be equal. They have to be for us to be minimizing cost. But what's happening in this problem is that the marginal costs are not equal. The firms are both still maximizing their profit. So from the firm's perspective, they're not doing anything wrong. It's just that that amount of output is being produced inefficiently. We can also extend this to the case where we have N firms. Here we've got 2 firms with different costs. We can extend it to the case where we have N firms with different marginal costs of production. You would go through the same process as before, and it's relatively straightforward. I'm not going to go through it here. We do need to talk about what comes out of that, though, and that is that if you go through a setting up marginal revenue equals marginal cost, similar to what we did over here. What you're going to be able to get is a statement that looks like this. P star minus CI over P star is equal to SI star over elasticity. Now, that should look familiar because this is the markup over marginal cost. That's the Lerner index. This is the Nash equilibrium price minus the marginal cost of firm I. This is for a particular firm. So this is his markup over marginal cost as a percentage of the price is equal to its market share divided by its elasticity. Now, let's think about what that means. That means that the bigger the elasticity of demand, which means that consumers react a lot, the bigger the elasticity of demand, the smaller the markup is going to be. Or the smaller the share of the market for a firm, the smaller its markup would be. The other side of that coin is the bigger the share, the bigger the markup, and the smaller the consumer's elasticity, the bigger the markup. So that's in terms of a firm level. We can also, I'm going to put a little line here, we can also do a little bit more algebra, which we don't need to go through, and we can come up with a statement at the industry level that's also very intuitive, and that looks like this. P star minus C, I'm going to put a bar above it because that's going to be a weighted average, divided by P star. So that's the Lerner index in terms of a weighted average of the costs for the firm. Remember, this is going to be industry level. And that ends up being equal to the Herfindahl-Hirschman index divided by the elasticity of demand. This is also intuitive because what it says is that as industry concentration increases, the markup in the industry is bigger, which makes sense. Industry concentration means fewer firms have more market power. And we get the same relationship to elasticity. The more elastic demand is, the more willing consumers are to move away from this good, the less the markup is going to be. So that gives you an idea, hopefully, of how this Cournot model works. What we're going to do in future videos is we're going to think about other models of oligopoly, and we'll be able to compare them to what we get from the Cournot model. So I'll see you in another video.